Now we'll see when there are multiple devices, how things will work out, okay. So how interrupt system will work, we will see. So what we can do is, so definitely you can understand one thing, when there is only one device, then we can, we can have this idea. What is that? We remember the interrupt service routines address in some place and we can go there directly, correct? Now processor also will have clarity that who is interrupting, because there is only one device. When there are multiple devices and if everything can generate an interrupt, how processor is going to do the stuff, we will see. However, processor will have again a circuit related to interrupt handling, correct? So that interrupt circuit is going to be connected to these cables like this. You can imagine like this, okay? Now this device is connected to the circuit, D2 is connected, D3, D4, everything. So now whenever D1 generates an interrupt, then that interrupt circuit is going to take care of some of the things. What is that? So this device is going to say that, my dear circuit, please tell the CPU that I am interrupting. Then after that the CPU can do whatever it wants, okay? But please inform. Similarly, other devices also can sometimes generate interrupts. Now we have to design this interrupt circuit. We will see that later. That's a separate thing. We are now seeing programmer perspective, okay? That's why I'm just giving few details. The only thing which I am missing here is, sir, how the circuit can be designed, right? Correct? That's a separate story. I will teach that in IO separately. But here our idea is, let's say we have a circuit. What that circuit does, we will see. What this circuit does is, first of all, the devices are going to know, otherwise the devices are going to know some addresses, A1, A2, A3, A4. Sir, what are they, sir? I will tell you. So every device should have some interrupt service routine, right? That means how to handle this device. Whenever device interrupts, then we have to service that device, right? That is nothing but for that we need a software, that is interrupt service routine. Already for keyboard we have seen how to write it also, correct? In the same way, D1, D2, D3, D4 are going to have interrupt service routines. So ISR D1, ISR D2, ISR D3, ISR D4. Let's say they are in main memory locations. Let's say D1 is in M1, D2 is in M2, and D3 is in M3, and D4 is in M4. Okay. Now we will see A1, A2, A3, A4. They are interrupt vectors. Interrupt vector means it is directly, otherwise indirectly, somehow related to, otherwise pointer to this interrupt service routines. Okay. Now example, one of the implementation which now we are using is like this. So let's say interrupt service vectors are stored in M1, M2, M3, M4. What we are going to do is, we are creating a table. This table is called interrupt vector table, okay, also known as interrupt vector table. This is one of the implementation. We can implement in so many ways. Finally, understand the concept. So here M1, M2, M3, M4 are stored in starting memory locations. Now let's call them A1, A2, A3, A4. Now these devices are going to be designed such a way that D1 is going to generate an interrupt along with the interrupts vector A1. Similarly, D2 is going to generate A2, D3 is going to generate A3, D4 is going to generate A4. So that this circuit's job will be easy. What is that? Now whenever interrupt comes to this circuit, then the circuit understands that A1 is the starting address. If I go to A1, then I will get the starting address of the interrupt service vector, interrupt service routine of that D1 in that way. So that circuit can easily understand, correct? So in that way, so we can design interrupt vectors. Here A1, A2, A3, A4 are called interrupt vectors. There is an alternative. What is that alternative is, rather than A1 points to M1, where M1 is the starting address of the interrupt service routine, what we can do is, we can do like this also, directly M1, M2, M3, M4. What's the problem with this one is, like, these are all implementation details. I can say that I cannot change these vectors now. Sorry, I cannot change these interrupt service routines. Once you hard code, otherwise once you design this kind of circuit, assume that designers decided to give device number 1 M1 address, D2 M2, D3 M3, D4 M4. Then later we cannot change these memory addresses, otherwise always we have to write interrupt service routines in these places only. We can't move them, correct? But if I write a just indirect pointer, that's obviously always you get advantage because of pointers. If you write A1, A2, A3, A4, and A1, A2, A3, A4 are fixed memory starting locations maybe, okay. Now here In these A1, A2, A3, A4, if you write the real addresses of starting locations of interrupt service routines, then we can have some flexibility. How, sir? Tomorrow one more device comes, okay, then easily I can add it. Second thing, suddenly I want to change the interrupt service routine D4's address somewhere. I want to keep here M5. Okay, here I want to write interrupt service routine for D4. I want to move it. Okay, then it's quite easy. Simply here I write M5, so that will be automatically adjusted, right? You get flexibility, whatever it is. Finally, so this A1, A2, A3, A4 are called interrupt vectors. Okay, they are either direct addresses of that interrupt service routines, otherwise they are pointer to the addresses of the interrupt service routines. That's it. That is about, multiple devices and handling them, correct? So now there are some more issues we have to talk about. One is how to have nested interrupts. What is nested interrupt? Example, let's say you are when you are executing a program, that means your processor is executing a program. Suddenly interrupt came. While executing that interrupt, one more interrupt came. Should we service the new interrupt? Otherwise, should we should not allow, right? There are two cases, correct? Sometimes when you are servicing the interrupt, then another interrupt comes, we have to accept. We need to accept. We should accept. Such case arises sometimes. Then we have to, then we say that we are allowing nested interrupts. That concept is called nested interrupt. Sometimes we have to allow them. Then how to handle them we will see. First of all, so one more detail we will see now. Let's summarize about this one first. After that we can go to nested interrupts. So when you have multiple devices, we are going to get what? Directly A1, A2, A3, A4. That means interrupt vectors. Through this table, we can get the memory addresses, right? M1, M2, M3, M5. Now, what is hardware support we are getting here? So here, interrupt mechanisms hardware is helping us in finding what? The appropriate memory location, correct? So this circuit, what it will do is, it will change the program counter by appropriate memory address. Example, let's say device number 1 interrupts. And at that time you are executing a program which is at 5000. We are busy doing something here. Okay, this line. After that we would like to go to, let us change this to as it is, M4. In the M4 we have interrupt service routine, let's say D4. Okay. Now, so after 5000 we are going to execute next instruction which is at 5004. Then we will be having link register. Now whenever interrupt comes, which is through A1, that means device 1, then so this circuit will directly index into this one, and this memory address will be fetched M1, then blindly that M1 will be written into program counter. Okay, now the 5004 will be stored in link register, right? That's it. This is the hardware part, I can say. Then remaining thing is as it is. Now, so as usual, processor has to execute what? Next instruction which is in program counter. Since it is M1, so this service routine will be executed, so device will be served, right? So in that way, so interrupts can be used, right? Now second thing, in this interrupt service routine we have to write it. See, there is a programmer responsibility also. What is this device responsibility or hardware responsibility? Hardware is allowing us to jump to automatically to interrupt service routine. But while coming back, we should go to appropriate. That's why here again your hardware is supporting us with one more instruction. What is that? Interrupt, return from interrupt, correct? Assume that there is an instruction called return from interrupt, and when you execute it, that instruction is designed such a way that it blindly will go to this link register. Since it is 5004, that will be moved here and we will come back to routine, right? So this is the way interrupts are, executed. Now, here I would like to tell you one more thing. What if you have nested interrupts? Will it work? This model will not work, right? Why? Let us try nested interrupts. Example, let's say first A1 is giving the interrupt. While you are servicing that interrupt, then A2 is coming, let's say. Before that, one more point I would like to tell you. This interrupt service routine should be designed very carefully. Okay, the person who writes device drivers, he should be very careful. What is that? Sir, why he should be careful? Is it not just simple program? It's a simple program, but here you can do some mistakes. Example, let's say this program, let's say we are executing some instruction at 5000, right? Before interrupt comes. Let's say we were executing at 5000. Then whenever interrupt comes, while at that time we were still, we are in between, right? We are in between. Then we, of course, but this circuit will delay us, because of this delay circuit, we are going to get the next address, which is M1 or whatever. But before that, remember one thing, this instruction will be completed first. Okay. So then only this circuit will start doing the functionality, and it will place M1 here. Okay. Then in the link register, next address, that means program counters next address 5004. So this is about this circuit, right? You understand that. Now apart from that, so in this interrupt service routine, we have to, we should do one extra step. I will tell you. That is, of course, it's a programming thing. I will tell you. Example, let's say this is the program you are executing. Let's call it as program 1. And currently we are executing at 5000. Now, when you are executing the program, there will be some registers which you are using, right? Let's call them R1, R2, R3. I did not talk about them, right, so far. This is also one more important aspect. Whenever interrupt occurs, at that time maybe you are using register 1, register 2, register 3, register 4. Then this interrupt service routine should not spoil them. That's quite easy. How, sir? Whenever you develop interrupt service routine, you do one thing. When you want, so what's the problem? Why you want to spoil it? Sir, I don't want to really spoil, but in my interrupt service routine, I need some temporary registers. Accidentally, if I take R1 or R2 or R3 or R4, then they are going to be spoiled, right? Then you don't do that. What you do is, so when you are designing this interrupt service routine, whatever the registers you use, example, if you want to use R1, R2, before that, simply, we have already system stack, right? In the system stack, example, you want to use R1, R2, right? Push R1's data, R2's data. Okay, stack pointer. First, remember them. Then, your interrupt service routine should use R1 and R2. Yeah, now you spoil them. No problem. Why, sir? I will tell you. You spoil whatever you do. Then once, whenever your interrupt service routine is done, whenever you are returning from the interrupt, before that, again, store the results back and come back. Okay, try to understand. So, use your own registers. Sir, but they are all public registers, right? That's why store them. The old data should be stored here using the stack pointer. That is the job of interrupt service routine. Okay. So here you don't get, any processor support. Of course, processor helps you, giving you stack pointer. Using the stack pointer, so remember that R1, R2, store them into stack. Once, your service is done, once you service the device. Now, when you are about to return from the interrupt, before that, simply store the results back. Then this program won't get disturbed because of interrupt service routine execution. Then because of return from interrupt, we will come to the normalcy, right? So that is one thing I would like to talk about. Second thing, program status register. This is, you should be careful. Program status register. Sir, what is program status? Also known as program status word. Okay. Otherwise, sorry, processor status word. Okay. I'm sorry, processor status. So there are some registers which represents processor status. Correct. What are they? There are a lot of bits. One of them is like, carry. Second one is negative. Did you remember? Z field. So these are the, processor status words. C, N, Z, V. Correct. Did you remember? Overflow bit. Otherwise this one 0 bit. Then negative bit. Carry out bit. Correct. Apart from that, there will be some other extra bits also, which we did not discuss because they were not relevant. But all that bits should be remembered, because example, let's say that bits are like the 1001. Then your interrupt service routine might spoil them. Correct. That's why generally in the stack pointer, of course, in the stack pointer you can store them, not a problem. But generally, majority of the architectures, what they do is the circuit itself will do that, because that is compulsory, right? That is compulsory. So that's why that interrupt, I can say this interrupt circuit is there, right? That circuit is going to automatically store this program status. Okay. So otherwise, not program status exactly. We say, specifically processor status. Okay. So processor status registers. And don't get confused between processor status registers and this general purpose registers. General purpose registers are like R1, R2, R3. We use for temporary additions, subtractions to store the results, correct? And program counter and stack pointer, link register, they are all general purpose registers. Now there are some specific registers already I told you, that is processor status registers. So they are already that contains n bit, z bit. These are all already right? Negative bit, 0 bit, overflow bit, and what is another thing? Carry out bit. Similarly, some other bits also there. So that bits we have to automatically, that means this circuit is going to automatically store. Now I have a question. What is that is? Why we have to store only these bits automatically? Why not these registers also? General purpose registers, because general purpose registers are huge in number. Now it takes lot of time. This is only everything only one bit, right? So it will be one or two registers. Only your processor status register contains flag bits, I can say. That is only one or two registers. It takes very less time. So that's why we do that. Sir, but why are you not doing this one? The reason is unnecessarily it wastes lot of time, correct? So because of that, efficiency will be reduced. But why to store them? Because what is the reason? Ask yourself. Why general purpose registers should not be stored by this automatic circuit? Very simple. Because the interrupt service routine which is going to come for execution, that is going to use only one or two registers, right? Correct? Maybe one or two or three. Such a way efficiently they will be implemented. So when that interrupt service routine is using only R1, R2, R3, and which is going to spoil only R1, R2, R3, which are nothing but general purpose registers, and stack pointer, maybe it might use stack pointer, correct? Maybe it might use link register. So whatever the registers you are going to use, only that will be spoiled, correct? Then interrupt service routine currently which is going to be executed, that knows everything about which is going to be spoiled. So better interrupt service routine takes care of that. Rather than that, if you say that, sir, whenever interrupt comes, automatically we save all the processor status. Second one, all the general purpose registers if you save, then unnecessarily you are wasting the lot of time. Now let us summarize. Whenever interrupt comes in most of the architectures, your interrupt circuit automatically does what? It automatically does saving the program counter, correct? That means next address, next instruction, we say that it saves the program counter. I will write. Okay, so one thing, this interrupt circuit is going to save program counter. Remember it. Second thing, what? Second thing is processor status, right? So processor status word, I can say. That means some one or two registers which are related to processor status. Already I told you, right? Negative, 0, everything. Now, the third one. One more thing what will be stored is, that's it, only these two. But not all registers, not all general purpose registers. Okay, remember it. It is wrong. Why? Because it takes a lot of time. Generally, architectures won't support. Now, really, if that registers get spoiled, who is going to spoil them? Interrupt service routine. Now this interrupt service routine should be designed. We should, as a programmer, let's say you are working in low level, means what? You are writing device driver, means you should write such a way that it should not spoil others code, right? So that interrupt service routines should be designed such a way that they should not spoil other programs. Okay, so that's why that what I can say is, rather than storing all the general purpose registers automatically, interrupt service routines are going to save only the registers which are going to used by this interrupt service routine. That's better, correct? Now I will give you an analogy for that. Example, let's say there is a village and the head is Serpent. He is the head of the village. These are all the various houses. Currently there are a lot of villagers who are staying in these houses. Now you are a movie director, okay? Now you want to do some shooting here. this village has some significance historically. Okay. Now, if you ask the Sarpanch, my dear Sarpanch, I want this village, then because you are a famous movie director, so he will give you chance and you can complete your shooting. After that, you have to give that village as it is. That is a requirement. Exactly, interrupt is also doing same thing. Whenever interrupt service routine executed, then that interrupt service routine is going to take the registers, correct? That because it's a program, it needs some temporary registers, but you should not spoil others. Maybe you might be taking, other registers which are currently using by this kind of villagers, correct? That means currently used by the old program. So here also same thing. Already some villagers are residing and they are living here. Then suddenly you become interrupt, right? Director become interrupt, and director want to do some shooting work, but he can use these houses, but he has to give that houses back like as it is. Okay, that is a requirement. Now here there are two things. One thing, Sarpanch can remember all these, like Sarpanch can maintain notes. In this house, what are the items they have, like number of items. Let's say he is maintaining for every house number of items, like so that he can take care of all the responsibility. So every house, this house number 1 has, let's say, 1 fridge, 1 TV. In that way, he is writing all the data. It takes lot of time because the village means there will be thousands of houses, right? That is one idea. Second idea, my dear Sarpanch, don't worry, don't do that. So movie director is doing like this. My dear Sarpanch, don't do. I will do. What I do is, because I am going to use only few houses, right? Occasionally I will be modifying, and I have a better clarity than you. If you have to maintain all that stuff, if you have to save all the household items information, then all the 1000 house address, 1000 houses information we have to maintain, you have to. But as a movie director, I have a better clarity. I will do like this. First of all, when example, let's say when I come to this house, really if I use anything here, then I note down, okay, about house number 10. Similarly, if I use any other house, I maintain the information, like I used a TV here, I used a fridge here, whatever, and I used some of the chocolates here, I ate them. Then director, whenever he leaves at that time, he has to keep as it is, correct? Yes, he can do it. So now there are two options, either Sarpanch can do it, otherwise this movie maker can do it. But which one is preferable? Sarpanch doesn't know which are going to be spoiled, then he will be saving unnecessarily all of them, right? So it takes lot of time. That's why better implementation is what? The general purpose registers, okay, like houses, okay, that general purpose register should be stored by, otherwise saved back by interrupt service routine rather than this interrupt circuit. If really this interrupt circuit has to do that, we can implement, but all the CPU registers he has to, because he doesn't have any clarity which registers this interrupt service routine is going to spoil. That's why he is not having the domain expertise. Then he will be unnecessarily saving all the processor registers, and again he is getting back, correct? Then how much time it will take? Definitely every register we have to store in the memory, then we have to bring it back. It takes lot of time, correct? That's why a good design generally won't do. But this interrupt circuit is going to only save processor status word, correct? Because that is only 1 word or 2 words, right? Maybe 8 bytes or 32 bits, otherwise 64, such kind of thing, depends on the architecture, right? So that's why it takes only 1 instruction time. That's not a problem. But to save 32 registers or 64 registers, it takes lot of time, right? 64 instructions required. Here only 1 instruction or 2 instructions, correct? Second thing, it is easy to do, right? Because only one, it takes only 1 nanosecond or 2 nanosecond, because only 1 status word. That's why. So interrupt circuits are going to do that task. Okay. Now, so this is all the story about multiple interrupts, correct? Now still some more questions we have to answer. What are these? Like what if sometimes your processor doesn't want to, that means some program doesn't want interrupts. Sir, we did not understand. What does it mean? Example, let's say you are executing a program. At that time you don't want to listen to the interrupts, because that is what your program, let's say your program is highly important program and it doesn't really require any interrupt. Such programs generally OS programs. Okay, so that kind of provision is required sometimes, and you are doing some very important thing like critical section kind of stuff you are doing. Then if interrupt comes, you should not bother, right? Then at that time, so we need a provision. Sir, how that kind of things will be handled? Do they, I mean, are they handled in high level, like in a programming level, otherwise hardware level? Yes, in hardware level you have a support for that. So every device and processor is going to have some control bits. So far we have not seen any control bit, right? Now I am going to tell you that control bits. Okay.